q mu p. Okay, so p extension meaning the order of the Galois group here is a power of p, and I denote this Galois group by A using class field theory. This is same as the p part of the ideal class group. Okay, and this Galois group is delta. So I can, if I think of this as p part of the ideal class group, then the Galois group of q mu p over q acts on the ideals. It takes principal ideals to principal ideals, so it acts on the Galois group. It acts on the ideal class group, and it takes elements of p power order to elements of p power order. So it acts on A. If I think of it as a Galois group of this h over q mu p, then there is a exact sequence given by from Galois theory, and okay, so h would be Galois over q, and then I can take any element of delta, lift it to an element in this Galois group, and let it act on this by conjugation. So this is similar to what we saw in Professor Froman's talk yesterday, where we had Z cover of S3 minus a naught, and then on top of that we had another group. So so we pick a lift here, let it act on this by conjugation, and that action matches with the previous action that's in terms of ideals. Okay, this action is independent of the lift because E is abelian. Okay, so we consider it as a module over ZP delta. So it's a ZP module, it's a delta module. So we look at it as a module over this group ring. And there is a canonical character of delta into ZP. So let me write it down once. So delta to Z mod PZ cross. So later I'll write down a p-adic version of this. So this takes delta to, so I have to tell you which number between 0 and p minus 1 this is. So I take a root of unity, and it takes it to omega delta. So that's what delta does. Okay, so this is what defines mu p. So that's the first map in there, and then the next one is just the Teichmüller lift. So given by Hensel's lemma. So that lands inside roots of p minus first roots of unity in ZP cross. So I can write any module as a direct sum decomposition like this. So this is just because p minus 1 is invertible in ZP. Okay, so I'll take the direct sum decomposition of A like this, and then Herbrand proved that if I is again there is a typo, sorry, 3 should be less than or equal to R.
The 4 will lift up. Okay.
Yes. Thank you. Yeah, so this is what it should be. I'm sorry about the typos. Then Herbrand proved that if AI is non-zero, so the ith component of this ideal class group is non-zero, then P divides the zeta value, okay, or equivalently this Bernoulli number. Whenever I say divides a rational number, I mean divides the numerator of the rational number. So again, let me point out there is a slight sort of twist here. So I have AI, and divisibility is for I plus 1 minus P. Okay, so this will sort of show in a somewhat ugly manner when I state the main conjecture of Iwasawa theory. But it's sort of already present here. Okay, so let me make some remarks. You can ask what about A1? So A1 is 0 always. This comes from the fact that the ideal class group of Q is trivial. More interestingly, what about even i's? And there is a conjecture of Van der Waals which says that AI is 0 for all even I. So this has been verified for, I don't know, few 100,000 up to primes of less than or equal to few 100,000. Not sure, million? Maybe.
Is that still conjectured?
Yes, that's still, I mean,
Is it believed?
not universally, I guess, but
Depends on whether you talk to the K-theorists or the people who do probabilistic number theory. So they have very different opinions.
I would guess it's wrong.
What are the different opinions? Who has which opinion?
Well, I shouldn't name names, but I know the K-theorists think the K-theory of Z would look so much nicer if it were true.
yeah, I think
It should be
Wishful
true.
thinking.
So that's a statistical.
yes,
That's what the statistics.
yeah.
Can you say again what a to power I is?
Oh, so this was just, I just write M as a direct sum of this as a ZP delta module. So Mi is just everything in M on which elements of delta act by this character. Okay? So this character takes values in ZP, so that makes sense. Okay. Okay, so okay, let me state the next thing. By the way, so if this were true, then the converse would follow from certain things that Kummer proved and Herbert proved. So, but this conjecture, as we just heard, it's not universally believed, and even if it's true, it must be very hard to prove. Fortunately, the converse was proven by Ribet without the conjecture of Van der Waals. So again, there's the typo because I just copied this first part from above. Okay, so it's the converse. So if P divides the numerator of this value, then AI is non-zero. Okay, so this theorem is much harder than Herbrandt's theorem, because from this divisibility you want to come up with elements in the ideal class group. So you want to come up with some cohomology classes, if you like. So it's much harder, and the proof involves modular forms. So this is a refinement of Kummer's criteria. Okay, Kummer's criteria was just that if P divides one of the Bernoulli numbers, then the ideal class group is the P part of the ideal class group is non-trivial. But this tells you precisely which part of the ideal class group is non-trivial, okay, depending on which Bernoulli number it divides, or the other way around. If that part of the ideal class group is non-trivial, then it divides that Bernoulli number. So the Herbrand-Ribet theorem is a sort of very strong refinement of Kummer's criteria by taking into account the action of the Galois group of Q mu P over Q. Okay. So for instance, the fact that 691 divides P12 or zeta minus 11 means that the corresponding, so 12 minus 691 component, 691 minus 12 component is the one that's non-zero for 691. Q mu 691. Okay, so then we come to Iwasawa. So you can ask, what happens if P squared divides the zeta values, or if P or higher powers of P divides the zeta values, or higher powers of P divide the order of these components. Okay, you can try to do this in the style of Ribet and Herbrand for a while, but then it becomes very cumbersome. So the great insight of Iwasawa was that instead of studying one field at a time, it's much nicer to study a whole tower of fields, and then not only does, because of the extra structure you get, the algebra somehow simplifies, and you can prove many results without even having any analytic invariants. So that is what I'll do first. So So there will be, first there will be some completely, an arithmetic result, and then we will bring in L functions into picture at a somewhat later point. Okay, so now I take F to be any number field. So any finite extension of Q. So this is my F0. Then I have F1, Fn, F infinity. This is union of Fn. So this is not a number field anymore. The Galois group of this is gamma n. This is isomorphic to Z mod P to the nz. And the whole Galois group I denote by gamma. This is isomorphic to Zp, the p-adic integers. So we look at this tower, and then on top of it, so let me stick to my notation. So I can look at ideal class groups of each of these, p part of the ideal class group of each of this, using class field theory. An alternate description would be I take L, this is the maximal abelian unramified pro P extension of F infinity, and the ideal and the Galois group of this is denoted by Y. Okay, so I can either think of this as P part of ideal class groups and then taking the inverse limit with respect to norm maps. So Y is, or using ideal class field theory, I can think of this as Galois group of L over F infinity. Okay, so so here Y is a, again by usual sort of by the thing that I said before, either with any description that you want, you get an action of gamma on Y, either through Galois theory or through actions on the ideal. The two actions match up. And then we want to study this Y as a module over gamma. Okay, so in fact it's a module because Y is compact. It's a module over this Iwasawa algebra, ZP double bracket T. So that's just inverse limit of these group rings. Okay, so these are these completed group rings. And this ring is much nicer than just the group ring, because at least once you fix a topological generator of gamma, we get a canonical isomorphism from this Iwasawa algebra to power series in one variable. So that's nice. So then at this point we can either just tensor this lambda with QP, and then it's a PID, and then we can define invariants like we saw in yesterday's talk, or we can sort of work slightly harder as Iwasawa did, and we can use the structure theory of finitely generated lambda modules. Okay, so if lambda were a PID, then we know that finitely generated modules over PIDs are exactly isomorphic to such things. So there is a free part and there is a torsion part. But lambda is not a PID. Nevertheless, it's a dimension 2 ring. So we get that any finitely generated module over lambda is pseudo-isomorphic to something like this, and pseudo-isomorphism just means that the kernel and co-kernel are pseudo-null. So in this case, pseudo-null just means finite. Okay, so there is a map like this with finite kernel and co-kernel. Or more general, there are more general, notions of pseudo-null modules over more general rings, but in this case it just means finite. Okay, so if I have a finitely generated torsion module, so the extra word here is torsion. Torsion means that the R there is 0, so M is pseudo-isomorphic to something like the basic torsion modules. Another way of saying that it's torsion is that for every M there is a non-zero element which annihilates that M, small m. Okay. Then I can define characteristic ideal of M. So these FIs are uniquely, well, not FIs, but the product of FIs and the ideal generated by them are uniquely determined by M. So it's a well-defined ideal. The FIs may change because you can have sort of like F1, F2. This is pseudo-isomorphic to F1 direct sum F2. Okay, one can have this. So, but the product is the ideal generated by the product is well defined, and so this is called a characteristic ideal of M. So throughout this talk, I'll sort of interchangeably use lambda to mean either the Iwasawa algebra or this power series ring. So implicitly what this means is that I'm going to fix a topological generator and then use this canonical isomorphism. Okay, so this characteristic ideal is an ideal in a power series ring in one variable. Okay, so I can take its generator and think of its coefficients. Okay, so this gives a nice invariant of finitely generated torsion lambda modules, and then this is these are two famous theorems of Iwasawa. Maybe they were proved slightly earlier, I think. Maybe they were announced slightly earlier, but I think in print they are from 1959. So he proved that this Y is a finitely generated torsion lambda module. So that's not hard to prove using some class field theory. But then the more sort of famous theorem is the second one, which gives I think this is the first result of its kind, which sort of gives some general result about ideal class groups. So it says that if the P part of the ideal class group has order P to the e to the n, then there is a nice formula for En. So P to the En, then there is a nice formula for En. So he defined three invariants for this tower. So these invariants are for this tower. So F infinity over F. So mu is mu of F infinity over F, lambda is lambda of F infinity over F, and this nu is nu of F infinity over F. So he attached three invariants to this tower, and then the orders have to satisfy this formula. Okay, so where do these invariants come from? So they come from the generator of the characteristic ideal of Y. Okay, so if I take the characteristic, if I take a generator of the characteristic ideal of Y, then mu is the largest. So f of t is just summation a n t to the n in ZP t. So mu is the largest power of p that divides all the ans, and so an by mu p to the n is in ZP, and lambda is the smallest non-negative integer such that p does not divide an by mu p, and then nu is some mysterious quantity that classical Iwasawa theory generally ignores. So this is a bit of self-advertisement with this theory of higher churn classes that we are trying to sort of develop, where this new sometimes shows up at the second churn class of some. So generally we sort of ignore that. But okay, so this is the formula. So how does so roughly how does the proof work? So the first theorem tells us that there is a non-trivial characteristic ideal, and then we just then we get that Y is pseudo-isomorphic to lambda mod F, and then we have to prove this result for F because the difference, the finite difference, will be absorbed by this quantity nu. Okay, so we have to prove such a formula for this, except that I haven't told you one thing, which is on the next slide. Okay. Okay. So you have to know how to go from Yn to An. So there is a simple way to go from Yn to An. So I take the co-invariance. So this is Y modulo 1 minus gamma to the p to the ny. There is a map from this to An. In some nice cases, this is an isomorphism, but in general, the kernel and co-kernel are obviously finite, but the order is bounded as n varies. Okay, so the order the order of the kernel and co-kernel stabilizes as n varies. So that's the reason why you can get a result about order of ans from Y. So this kind of theorems are usually referred to as control theorems in Iwasawa theory. So by studying some profinite object, you get information about some finite level objects.
And why is Y pseudo-isomorphic to lambda mod F? Was it not a finite product of such
Oh,
things?
so because of such things, I can always write it as. But yeah, I mean, in general.
Is it true if F1 is equal to F2? No, that is not true. If I take F1 equal to P and F2 equal to P,
It's not isomorphic, it's pseudo-isomorphic.
yeah, but it is not true. It is just nonsense. It is just completely wrong. One is annihilated. If everything is equal to F2, it is not true. One is annihilated by the F, the other is not annihilated by F squared, by F.
I think what you have in mind is they are equal in K naught, not isomorphic.
That's actually
I mean, that's already true. It's already wrong for PIDs. What do you expect?
No, but for,
Zemo 4 is
no, but that's for PID we want an isomorph. Okay, let me write it like this. So then we have to prove it for individual and powers of irreducible.
Okay.
Okay. All right.
Sorry to interrupt. Sorry.
Sorry.
Mahesh, maybe
yeah.
one other question.
Yeah.
In the theory you guys are developing, do you have an interpretation there for the nu as well? The constant?
So whenever mu and lambda are both 0, nu is the second churn class of
That's
the
also a
module.
challenge on that.
Yes.
So nu does not depend on F, right?
Nu, no, it only depends on the module. Yeah, but I mean, we only have the interpretation in the special case when mu and lambda are 0, so the f's all have to be units. Okay, so there, I mean, okay, so Iwasawa had this nice result, but then so he computed mu and lambda for lots of ZP extensions. Yet I haven't told you that there are ZP extensions. So as of now, all these may be vacuous results, but we'll see an example of ZP extensions soon. There are lots of ZP extensions for number fields, and Iwasawa computed many of these lambdas and mu in general, for these examples.